Welcome to the tutorial on security and privacy in distributed optimization and learning. My name is Nitin Vaidya from Georgetown University. Before I start, let me inform you that the slides for this tutorial will be posted on my website. And in fact, I have already posted a longer version of most of this tutorial on the website. And I plan to add some more lectures to that over time. So let's start with the notion of distributed optimization that we are going to be looking at in this tutorial. So I'll take an example for this. Consider three people or three agents that are located in this space, and they want to meet, let's say for dinner, and they need to pick a place to meet for dinner. And so you can imagine many different ways of choosing the right place. But the way we will do in the context of this tutorial is that we will define a cost function for each of these agents. And so the three people, number 1, 2, and 3, and depending on which location X they meet at, each of them will have a certain cost of getting to that location X. So the cost may represent the time it takes them to get to that location X. It could represent the actual cost in dollars, if for example, they are going to take a taxi or something like that. And so f1 of X is the cost function for agent 1 for location X, and f2x is the cost function for agent 2, and so on. And then the goal is to choose a location where the total cost over all the agents is minimized. In particular, you want to minimize the cost function shown here, this particular cost function, and we want to compute the argument X that minimizes this cost function. That's what this argmin represents. Now, the argmin could be computed over the entire space, meaning we may not have a constraint on X, or in general, we may actually impose a constraint on X. So both versions of the problem are of interest. We won't get into too much detail in this particular tutorial, but the algorithms can change a little bit depending on whether there is a constraint or not. So for example, on the bottom right, it says X belongs to a set X. That would be a constraint. So anyhow, this is just a very simple example of the optimization problem. Now, when I write my formula expressions, I may or may not specify the constraint explicitly. And like I said, we are not going to get into any of the algorithms, or certainly not the proofs in any detail. So we can gloss over some details of the arguments in this particular tutorial. So let's take another example of a cost function for the distributed optimization problem. So let's say you want to solve the distributed linear regression problem, where perhaps each agent I knows a data point, which is characterized by this vector AI and a real value yi. And this AI and yi may be related through an expression such as yi equal to ai x star plus some noise epsilon I. The agent knows ai and yi, and the goal is to compute an x that approximates or represents this particular relationship as accurately as possible. And one way to try to estimate that x star may be to define a cost function fix for agent I as yi minus aix square, and then we minimize the cost over all the agents. So yi minus aix is sort of the error in the estimation. In machine learning as well, cost functions such as these arise quite naturally. So we know that in machine learning, we have some data that we're going to use to train a network, maybe a neural network or a support vector machine. So let's take the example of training a neural network to build a classifier. And so what we start with is some data. In this case, the data is an image, and DI is the image, or DJ is the image, and YJ is the class for that image. So the class could be bird, car, things like that. So here's an example of an image or picture of cats, and the class is cat. And when we train the neural network, the goal is to determine the parameters of the neural network, such as the one that is shown here. And what's going to happen is that we apply the input, in this case, the picture, as to the neural network. And what the neural network is going to produce for you is basically some representation of the class. So it's going to estimate the class for us, hopefully accurately. And of course, the classification may not be accurate all the time, not for all the data, in which case we will define the so-called loss function. The exact detail of the loss function are not important, but here on the slide I have shown one. But the loss characterizes effectively, how well or how poorly the neural network classifies my data, training data. And then the goal during training will be to minimize the total loss over all the data that we have. And so the cost function here as well has the similar structure to the one that we saw. We're trying to find the argument that minimizes summation of a number of cost functions, sigma fi, in this case called li because it's loss function. Now, when we train neural networks, the algorithms that we use routinely don't have to be distributed, but one can do this distributedly as well, meaning that we may have a system where the data is distributed naturally across many agents. For example, the agent might be my phone, and the phone itself has some data that is to be used during training, and each phone has its own data. And what we want to do perhaps is to use the data in a distributed way without having to bring all the data in one place for the purpose of training a network. And that's the kind of distributed learning problem that we want to look at. And in this setting, because the data is distributed, you can imagine that there exists a cost function such as fix that captures the loss corresponding to the data that is available to agent I. So each agent has its own loss function. And then the goal would be to minimize the global loss, which is the loss over all the agents. And I want to compute the parameter x, which represents the weights and biases of the neural network, such that x will minimize my global loss function. So these sorts of cost functions appear in many settings, not just machine learning. And because of that, there has been many, many years of research on designing algorithms to distributedly minimize cost functions of this form. We're going to assume for convenience that these cost functions are convex, but a lot of the ideas I'm going to introduce here have been used in the settings when the function may not be convex. But if you do have a cost function that is convex, and the minimization algorithm is intuitively quite simple, this picture illustrates such a cost function. And what we do in this setting is that we initially guess the minimum argument, the argument that minimizes the cost function, let's say it's x0. So we're going to start at x0 and then try to improve that estimate of the minimum. So we want to go from x0 and improve it to x1. From x1, we want to improve it to x2 and so on. And the way this gradient method works is that you start with an estimate of the minimum, and then we take a step in the direction that is determined by the gradient. It's negative, opposite of the gradient. And by doing this computation, we can compute the next estimate, xk plus 1. So from x0, we can get x1. From x1, we can get x2. And then if we use this constant that are called, well, this is lambda k, it could depend on k. So it may or may not be a constant. But if you choose this lambda, so-called step size, properly, then over time, this algorithm will converge the estimate to the true minimum of the cost function. And so we're going to use algorithms like this. In this case, note that we are having to use the gradient of the cost function in order to compute the new estimate. Now, if the cost function is of the form that we are interested in, right, the cost function that we saw, fx was equal to a summation of a number of cost functions, sigma fix, where I is the index of the agent, then the gradient you need to use is the gradient of this particular cost function, summation fi of x, which equivalently can be written as summation of the gradient of individual fi of x. Now, the difficulty is that this cost function fi is known only to agent I. It's private to agent I. The other agents don't necessarily know it. And yet I need to compute this summation of the gradients over all the agents. And that's why we need some cooperation between these agents to be able to perform the optimization of this sigma fi of x. No single agent can do this, and we need some cooperative or distributed algorithms for achieving that goal. So the distributed optimization problem has been studied in two different architectures, broadly speaking. One is a server-based architecture where there is one server or perhaps multiple servers, that help these agents cooperate with each other towards the goal of minimizing the cost function sigma fi of x. Alternatively, we may have a peer-to-peer architecture such as the one shown in the top left, where there is no server centralized entity that is helping these agents to minimize the cost function. The agents form a network of their own. In this case, the network consists of 5 agents connected using the links shown here. But the agents have to use that network, use that communication mechanism to cooperate with each other so as to minimize the global cost function sigma fx. Again, without having to rely or without being able to rely on a centralized server. So for the most part, we will talk about this architecture, but some of the ideas I'm going to present have been applied to both the settings. So if you look at the literature, there are many versions of this distributed algorithm. Sometimes they're called distributed, sometimes federated, sometimes decentralized. And when people call something federated, they mean a particular way of using the server. For lack of time, I'm not going to go into all the variations. I'll introduce ideas somewhat broadly, but the ideas introduced for distributed server-based architecture will be applicable for other settings too, perhaps with some modifications. So we just don't have enough time to get into everything in great detail today. So if you take the server-based architecture, this is how you might perform the distributed optimization. The server is the one that is going to maintain this estimate, xk, of the minimum of the global cost function, sigma fi of x. And so initially the server has an initial guess, let's call it x0, and then the server is going to cooperate with the agents and then compute from there x1, and then from x1 it will compute x2 and so on. And as time proceeds, xk will converge to the true minimum of the cost function. That's the idea. So server maintains the estimate xk. Initially it's x0, and then in each iteration, the server sends the current estimate to all the agents. So the agents then receive the estimate from the server, all of them. And then they send back to the server the gradient of their local cost function at that estimate. So for example, if this is agent number 1, then it sends back to the server gradient of function f1, cost function f1 at xk. This is agent 2, this is agent 3. So similarly, agent 3 sends back gradient of its own cost function and agent 2 as well. So having received all the gradients, the server's job is quite easy. It adds up all the gradients. So that gives you the gradient of the global cost function, sigma fi x. And then it performs that step that we saw earlier. This is the current estimate. We take a step in the direction opposite to the gradient, and then we compute the next estimate. And then we repeat this. And with time, the algorithm will converge to the true minimum under reasonable assumptions about this lambda, the step size, and so on. Now, this algorithm is very simple in that the server is able to talk to all the agents. It's synchronous because it gets information from everybody in the form of the gradients. And therefore, the algorithm, in fact, simulates the algorithm that we saw earlier on the previous slides. It just implements it at the server with the cooperation of the agents, but it's almost equivalent to the server knowing all the cost functions. Although it doesn't, but it's equivalent to that. In reality, we don't want to use that particular algorithm because it's synchronous. You have to wait for everybody before you can take the next step. So synchronous algorithms can be slow, particularly when maybe 1 or 2 agents happen to be slow occasionally, then everybody has to wait for them. You also need, in this case, a gradient of individual cost functions. And if the cost function itself is, for example, a loss function over a lot of data, then computing the gradient could also be very expensive because there is a lot of data available. And there are stochastic variations in the algorithm that are also used in practice to avoid synchrony. There are asynchronous algorithms. And then there are other optimizations such as compressing those gradients. Instead of sending the whole gradient to the server, maybe you can send some compressed version of it to save communication costs. We won't get into any of these variations in the tutorial today. I want to give you quickly an example of a peer-to-peer algorithm as well. The server-based algorithm we saw does not give you security or privacy. That we will come to soon. But for now, let's just talk about how to do optimization in the peer-to-peer setting. So again, we are going to take a peer-to-peer iterative algorithm for the peer-to-peer network. similar to the server that was maintaining an estimate of the true minimum. Now each agent will maintain its own estimate of the true minimum of the global cost function, sigma fix. Even though each agent only knows its own cost function, over time, they will learn the argmin of the global cost function, sigma fix. The high-level structure is that each agent maintains its own estimate of this global minimum, and in each iteration, the agent will exchange its own estimate with its neighbors, and then compute a new estimate. And you repeat the process, and over time, every agent's estimate will become identical or approximately equal. And in the limit, they actually become equal. And as time progresses, their estimate will converge towards the true minimum of the global cost function. So let's take an example of an algorithm, a simple algorithm. In this case, 3 agents, x1, x2, rather agents 1, 2, and 3. This is agent 1, agent 2, agent 3. And they're connected by this simple network. Agent 1 is connected to agent 3, agent 3 is connected to agent 2. And like I said earlier, each agent maintains its own estimate. Let's call those estimates x1, x2, x3. The notation I'm using here is slightly different from the notation before. Here, the subscript is actually the agent's identifier. I think I used subscript previously as time. But the general idea is, like I said earlier, the agent will send his estimate to the neighbors. Like in this case, x3 is being sent to agents 1 and 2. Why 1 and 2? Because agent 3 is connected to 1 and 2 both. On the other hand, if I'm agent 1, then I will send my estimate only to agent 3 because only agent 3 is my neighbor. So the nodes only send information to their neighbors in this network. And like I said earlier, I'm changing the notation a little bit. So in this discussion of the peer-to-peer algorithm, the subscript is the agent ID, and in the bracket, I have the iteration index. So having obtained the estimate of the neighbors, then each agent performs this computation to compute its next estimate. So we were looking at agent number 1 now. So what does agent number 1 have? He has his own value of the estimate, suppose at time t, at the end of t iterations. And he has obtained the estimate from the neighbor, in this case, agent 3, at the current time, meaning at the end of t iterations. And the agent, in this case, agent 1, is able to compute the gradient of his own cost function at his own estimate because he knows both of them. And so what agent 1 is going to do is to take this step, meaning compute the new estimate as, first of all, this is a weighted average of the estimates it knows, its own estimate and the neighbor's estimate. It's a weighted average. The weights are non-negative, they add up to 1, and the weights are chosen carefully. I'll tell you how later on. And then this term is kind of like the term we saw earlier, where we took a step in the negative direction of the gradient. The key difference is that the gradient used here is the gradient of the cost function known to agent 1, not the global cost function. And even though each agent is going to do something like this, over time, they will actually minimize the global cost function. So what does agent 3 do? Similarly, it computes a weighted average with weights chosen carefully of his own estimate, which is this x3 of t, and the estimates received from agents 1 and 2. In this case, agents 1 and 2 are both neighbors of agent 3, and therefore agent 3 has all the 3 estimates. And then this is the term that consists of the gradient of the cost function f3 that is known to agent 3, at the estimate x3t that is also known to agent 3. So each agent can only use information that is known to itself and the estimates received from the neighbors. And x2 will do a similar update of its own estimate. Or rather, agent 2 will do a similar update of its own estimate, x2, which I have not written here explicitly. And one can show that if the weights, here the weights are, these are the weights in this weighted average. If these weights are chosen carefully, then in the limit as t approaches infinity, all the agents get converged to the same estimate. And in fact, that estimate happens to be an argmin of the global cost function. This is what we cared about. Now, what does it mean to choose the weights appropriately? What we need is that these weights should, if you write them as a matrix, where element wij is the weight assigned by agent I to agent j. For example, you can think of this as w11, and this would be W13 because that's the weight assigned by agent 1 to agent 3. W12 is actually 0 because the second estimate is x2 is not even appearing in this expression, which is like saying that I'm multiplying that estimate by 0. So if you form that matrix, then that matrix should be doubly stochastic, meaning that the rows and the columns should be non-negative and add up to 1. If each row adds up to a 1, each column adds up to a 1, and the numbers are non-negative. And if the graph is connected, the network, they're assuming the network is undirected. And if it is connected, if you have those two properties, then this algorithm will converge to the true minimum in the limit. There are a few other technical assumptions to be made, which I'm not going to state here. So why does it work? I'm not going to discuss that today. The proof is not that complicated, but we don't have time for it, unfortunately. So the focus of this tutorial really is on two challenges. And in fact, I'm going to focus on the first challenge for the most part, and then briefly discuss the second one. So the first challenge is security, or what I tend to call fault tolerance. But the main question we are addressing here is what happens if the clients are somehow misbehaving. A client might be client as in one of the agents. The agent might be misbehaving because maybe it's a compromised entity. Somebody has taken over the computer or the agent, security compromise, or it may be faulty. Maybe there's a software bug or hardware failure that's causing it to misbehave and send incorrect information. So in this case, in the server architecture, in the algorithm that we saw earlier, the agent has to supply gradients to the server. And what a compromise or a faulty agent might do is to send basically bad values for these gradients. And the question then becomes, what happens if the server is receiving such bad values? Will the algorithm work correctly? You should be able to guess that it shouldn't work correctly just because, I'm getting all this bad information and the server is just adding up all the gradients. If one of the gradients is bogus, of course, that summation will have no particular meaning. And so the algorithm shouldn't work correctly, at least the way it was stated. So the question then becomes, what do you do when you have compromise of agents in the system? The twin problem here is privacy. And now we are not worried about anybody tampering information, but we are worried about somebody learning my information. So for example, if I'm one of the agents and I'm using my data to train a neural network, perhaps I don't want the server to learn my data. And yet I want to collaborate with all the other agents to minimize the global cost function. Or if you think of the sigma FIX formulation, I don't want the server to know my cost function. If I'm agent 1, I don't want the server to know F1 of X. And yet we want to minimize sigma Fi of X. And so that's the privacy challenge. So this is a special case of a general problem, the multi-party privacy preserving computation. But there's a particular case, and then you can apply a solution that are designed for this particular instance of the problem. If you recall the problem of meeting, in our example, we had 3 people trying to get together for dinner. We had this cost function summation sigma Fi of X that we wanted to minimize to compute the location where they should meet, such that the total cost overall the agent is minimized. Now, in our initial discussion, we assumed that all the agents in the system are fault-free or good. But let's now consider the case where one of the agents may actually be behaving badly. In particular, agent 3 may be behaving badly. Now, if you try to minimize the summation of cost functions F1, F2, and F3, that might lead to undesirable outcome, because what this agent 3 might pretend is that the cost of meeting for that agent at the location where they want to go, perhaps their own location, is very low, but the cost is very high everywhere else. I don't know if you can see this blue curve, but what I'm suggesting here is that the cost of meeting anywhere but the location of the agent could be claimed to be very high. And then if you try to minimize the summation of the 3 cost functions, then the minimum, the argmin for the global cost function, summation sigma Fix, will end up somewhere quite close to the current location of this bad agent. And by behaving in this manner, the agent can influence, the bad agent can influence the outcome of the distributed computation quite significantly. And then the question becomes, can we somehow mitigate this impact of faulty agents or compromised agents. Same issue arises in the context of distributed machine learning as well. As we saw earlier, in a setting where the data might be distributed across different agents, or different agents are cooperating to train a machine model together, a faulty agent can misbehave and, for example, provide incorrect gradients during that distributed computation that we saw previously. And by doing that, it can influence the outcome of the computation, which in this case would be the model parameters for the machine that we are training. And so goal would be to try to eliminate the impact of faulty agents, and if we cannot eliminate it, somehow make it less severe, mitigate it. So we have been working on this problem in my group since 2015. There are other groups working on this problem as well. And I'm going to discuss some basic results in this space and then give you examples of distributed algorithms that have been developed primarily for the server-based architecture in the context of fault-tolerant or secure optimization. So we'll overview a few solutions that have been proposed as well. So before we can discuss the algorithms, first question is, what is it that we are trying to achieve? We do want to achieve fault tolerance. We want to survive bad behavior of faulty or compromised agents. But what does that exactly mean? What's the precise objective? So here is the objective that we defined some years ago. Remember that we have a number of agents. Suppose there are n agents, up to t of which perhaps could be bad or faulty or compromised. I'll just say they're faulty. In fact, we use the term Byzantine faulty in this literature to identify the bad agents. And the word Byzantine the term Byzantine fault is intended to point to the possibility that the faulty nodes can behave completely arbitrarily without limitations on their behavior. In fact, we allow faulty agents to even cooperate with each other free of cost, meaning they can magically talk to each other without having to worry about communication delay and things like that. So these algorithms are designed to tolerate worst case behavior from the compromised agents. And that's captured using this so-called Byzantine fault model in distributed computing literature. So the goal for the fault-tolerant optimization then is to optimize the cost, the summation of the local cost of just the good agents. Let's suppose a set of good agents is called G, then the goal will be to minimize this cost, which is summation over just the good agents. Now, the difficulty, of course, is that we don't know who the good agents are, and yet we want to achieve this objective. So in case of the rendezvous problem, where we have three people wanting to meet, if agent 3 is faulty, then what you want to minimize is cost function f1 plus f2, without actually knowing that agent 3 is faulty. So if I'm agent 1, I do not know that agent 3 is faulty, or is it agent 2 faulty, or maybe none of them is faulty. I don't know any of this, and yet my goal is to minimize f1 plus f2. For the machine learning setting, something similar. This global cost function was actually the loss aggregated over all the agents. There are 4 agents here, but if agent 2 were to be faulty, then I want to minimize the loss over just the 3 good agents, f1 plus f3 plus f4, and compute the x that minimizes that loss. The question really is that, is this really possible? It's a nice objective. The objective of minimizing cost of just the good guys sort of makes sense. Can we do this? The answer is that it actually depends. And it depends on what? So it depends on the cost functions themselves. So there's a spectrum of properties these cost functions might satisfy. On one extreme, the cost functions might be independent in the sense that knowing one of the cost functions or knowing some of the cost functions of some of the agents tells us nothing about the cost functions of other agents in the system. So that's what I mean by independence. There are no assumptions that we can make about the cost functions that help us learn something about one cost function if we know all the remaining cost functions, in fact. So that's one extreme. At the other extreme, the functions may have a lot of redundancy. For example, all the cost functions may actually be identical, which is to say, we may have f1 equal to f2 of x, equal to f3 of x, and so on. That's a very extreme example of redundancy, but then there is a whole spectrum in between, where the functions may incorporate some redundancy, some correlation, without actually being all identical. And whether we can satisfy this, we can solve this problem of computing argmin of sigma fi of x, where I correspond to just the good agents, that just depends on the property of the cost functions, and we are going to see soon what that property might be. So let's start with the case when there is no redundancy in the cost functions, and then we'll come to the case where there is redundancy. When there is redundancy, we will, in fact, discuss two variations on the theme there. In one case, we want to solve the objective at the top there exactly, without any approximation, whereas the other possibility is that we may, in fact, approximate this objective instead of solving it exactly. And I'll discuss both of them. We'll discuss exact resilience in a bit more detail than approximate resilience. So let's start with the first case, the independent functions. And here's an example where the argument x is a scalar, just a single real number. And what we have is three agents who want to meet somewhere on this street. So x denotes where on this street they are going to meet. And we have three agents, let's just call them A, B, and C, which happen to be at these locations A, B, and C to begin with, and they need to meet. And if, let's say we want to meet at this location X, then this cost function, the height of this function here tells you the cost for agent B to get to that location X from wherever it is right now. And similarly, the other cost functions are designed. And now, suppose I'm agent A, the first agent on the left here. And so we have three agents. And suppose that we want to design the algorithm to tolerate one bad agent, up to one bad agent. So which means that agent A has to allow for the possibility that one of these agents is faulty or misbehaving. Now, if agent C is misbehaving, then to satisfy our objective that we set out previously, to minimize the cost over just the good guys, we need to minimize the sum of these two cost functions that I've shown here and ignore the third cost function, and which would mean that we need to meet somewhere at this blue location, the location shown by the blue dot. On the other hand, if it were the case that agent B is actually faulty, then if you minimize these two costs, then the optimal X would be somewhere here. Now, the difficulty is that agent A actually doesn't know which of these two agents is faulty, B or C, or either one, actually. Maybe neither of them is faulty. And yet, depending on who is faulty, you have to meet either here or here. And no matter where agent A decides to go, the decision could be wrong depending on who is actually faulty. So it's a very simple argument to show that if the functions are independent, then it's actually impossible to achieve this objective of computing the argmin of sigma f(x) over just the good guys. So if you cannot achieve our original objective, then question is, what can you do? We cannot just declare defeat and walk away. Something has to be done. These people need to meet. So how do you compute the output? So first thing to observe quickly is that this is what we wanted to compute, but this is exactly equal to argmin of the average of the cost functions of the good agents, where actually it's a weighted average of the good cost functions, where the weights are uniform, meaning identical. Right, so each of them gets the weight of 1 over g, which is the size of set g. And so what we wanted to compute was an argmin, was the value of x that minimizes the uniformly weighted average of the good cost functions. And we just concluded that that's not actually possible. So the question then becomes, if we cannot do this, then can I sort of weaken my goal and minimize a non-uniformly weighted average of the good cost functions, which is to say, I minimize the weighted average where the weights are not necessarily all equal. Turns out that that's actually achievable. And the way we can do that is using an algorithm that looks similar to what we had before, right? This is the algorithm we saw previously, where the server maintains an estimate, and the estimate, in this case xk, is sent to the agents. Agents will send back to the server gradients of their own cost functions, and then the server takes this step to compute the new estimate xk plus 1. Except that now, if agent 3 happens to be faulty, then aggregating the gradients here will lead to incorrect outcome, because agent 3 can send bogus gradients because it's compromised or faulty. And so we don't want to just do a simple summation. We need to somehow get rid of the bad influence of the faulty gradient. And what we're going to do is to use a filtered gradient, meaning what the server will do is to receive all these gradients, right? There are n of them, n agents send n gradients, and the server will apply some transformation or a filter to those gradients, to those n gradients, and use the output of that filter in this step instead of just a summation of all the gradients. Now, what I've not told you is how this filtering happens. And in fact, there are many solutions proposed by now, which all look like this, in the sense the structure is the same, but the key difference is in the exact filter that they use. And I'm going to discuss some filters later on. But the filter that was introduced initially in the earliest work that I know of on distributed fault-tolerant optimization was designed specifically for scalar arguments, and the filter is as summarized on this slide. And I'm going to come to this filter again in a few minutes, and we'll take a simple example of this. But the basic idea is that the server, having received the n gradients, throws away the outliers. So there are n agents of which up to t might be faulty. So the server just sorts the gradients. The gradients are just real numbers, throws away the smallest and the largest t values, and just uses the average of the remaining n minus 2t as the filter gradient, or you can use the sum here. Doesn't really change the outcome of the algorithm in any significant way. And that's what we use in this particular step. And this gives you some desirable properties. So it in fact gives you, so this is an iterative algorithm. This is what happens in one iteration, and then the iteration is repeated many times. So the algorithm converges to an xk, right, such that that xk value becomes the argmin, or is approximately equal to the argmin of summation of the, actually argmin of a weighted average of the good cost functions. And those weights have certain properties. One property is that some of the weights may be zero, in fact. In particular, up to t good agents may end up with weight equal to zero. Weighted average uses a weight or multiplier for each cost function. The weight is going to be non-negative by design, but it may end up being zero. And this algorithm that I just showed you may attach weight of 0 to t up to t agents. What does weight equal to 0 mean? It just means that in effect, if there are a bunch of us trying to go for dinner, and if you give my cost function weight of 0, you're basically ignoring my opinion about where to go for dinner. My information is completely ignored in the computation. And this is saying that up to t good agents may get a weight of 0. All bad agents necessarily get a weight of 0 as well, which is good because we want to get rid of the influence of bad agents. Now, what about, so the t good agents, there are t potentially up to t bad agents. So there are at least n minus 2t remaining good agents. And in fact, let's take the case where exactly t agents happen to be bad. Then the remaining n minus 2t agents for this algorithm that I just showed you get roughly uniform weight. In particular, you can guarantee that the weight, uniform would be 1 over n minus 2t for those n minus 2t agents, the weight exactly equal to that. But instead, we can show that the weight is at least as large as that, which is a factor of 2 actually of the ideal value. So in summary, what that algorithm produces is argmin of a weighted average, where weight of good cost function I, ith good cost function is alpha I. The weight for bad functions is all 0. Up to t of the alpha i's might be equal to 0, up to t, not necessarily equal to t. And the rest of them will get roughly uniform weight. Now, it turns out that this is what we achieve with the algorithm I showed you. And in fact, this property that t good agents may have value 0, weight equal to 0, is something fundamental. No algorithm can avoid this outcome, meaning that no matter which algorithm you use for this problem, it may happen that T of the agents get the weight of 0. Now, the results I showed you were for the case where the argument is a scalar. What about the case when the argument is a vector? For example, for machine learning, the argument X is actually all the weights and biases in that machine, in the neural network. There could be a lot of those, thousands, maybe hundreds of thousands, millions. Now, it turns out that in that setting, the number of agents that may get the weight of 0 actually grows linearly with the dimension, which is not very nice because B could be very large. And we are ignoring the opinion or the cost functions of too many agents in the system. But that's for the case where the functions are arbitrary or independent. It turns out that in reality, these functions may not necessarily be arbitrary or independent of each other. There may be some dependence across them. For example, in the case of machine learning, you might even have the situation that all the agents behave identically. Their cost functions are basically the same. The loss functions are basically identical. But in more general settings, the cost functions or the loss functions may be related to each other, somehow dependent on each other. And if you have such redundancy or dependence, then we get better outcome, meaning we don't have to sacrifice so much. So that's what we're going to talk about next. Let's talk about functions with redundancy. And like I said, there are two versions of it, the exact resilience and approximate resilience. Let's talk about exact resilience first. So T is the number of faulty agents we want to tolerate, up to T. And let's define exact resilience as the following requirement, that we want to compute this argmin of the global cost over all the good agents, even though there are T faulty agents in the system or up to T faulty agents in the system. And earlier for the independent functions, we said this actually is not achievable. So clearly we'll have to make some assumptions now if you want to achieve this particular property of T resilience. So there's a trivial example that will show you that this T resilience is in fact achievable, in particular when you have full replication. Imagine that all the cost functions, meaning fi of x equal to fj of x, they're identical for all ij, right? Every agent's cost function is the same as the other agent's cost function. Now this may seem very strong, but let's take the example of going for dinner. Imagine that we are all meeting in a conference room physically right now, and we want to go for dinner from there. Then of course we're all starting from the same location, going to the same location. The cost functions will be identical. In that trivial case, minimizing the summation of the cost function over the good guys is equivalent to minimizing any individual good agent's cost function. So then the problem is trivially solvable. Each agent can minimize his own cost function and choose that as the output. Right, so it's a fairly simple way to solve the problem. In the context of that server-based architecture I showed you, the solution is also quite trivial, where the agents supply the gradients to the server, for the current value of xk. Bad agents may provide bad gradient. These could be bogus values, but the good agents all provide the correct gradient of their own cost function. But because the cost functions are all identical, the gradient supplied by agents 1 and 2 in this example will be identical. And so long as non-faulty agents are in the majority, all the server has to do is to apply a majority vote to the gradients it receives from the agents and use that majority in this step. So that's the filter. It's simply computing majority over the gradients. Now, it may seem that this particular case where all functions are identical is a bit too extreme, and that's in fact true. It's rare to have this formulation. In fact, we're going to show more general settings where T resilience is achievable. However, I want to point out that there are in fact cases where the cost functions of all the agents are in fact identical, and yet the problem is interesting. I'll come back to this later today when we talk about fault-tolerant stochastic learning briefly. But the basic idea there, just to give you a quick summary, is that all the agents are identical in the sense that the gradients they produce are coming from the same distribution. We're going to focus in this setting on stochastic learning or stochastic gradient optimization. And stochastic just means that the gradient that the agent is computing is not the actual gradient of the cost function, but an estimate And the problem becomes interesting here is that because even if all the agents are identical, their estimates may not be identical because these are randomized algorithms. So the stochastic gradients are not identical, even if their expectations of the stochastic gradients are identical. And that makes the problem non-trivial, actually. Unlike this majority setting where the gradients were exact, right? I'm taking the gradient of the cost function f1, not the stochastic gradient. But stochastic gradient will make this case of full replication also interesting. But here is the result. We will defer stochastic gradient for later. So the result here says that T resilience is achievable if and only if cost functions satisfy something called 2T redundancy. So what is 2T redundancy? It's a very simple property. Again, we have n agents of which T might be faulty. And so the property requires that 2T redundancy property requires that the argmin of the sum of any n minus 2T cost functions should be equal to the argmin of the sum of all the cost functions. Okay, so this is a requirement. Mathematically, if you write it, it's the same thing on the previous slide. Set S is a set of all agents for non-faulty agents, and this is a set of any n minus 2T good agents, and those two have to be the same. In that case, the property of T resilience is achievable. Here is a centralized algorithm for it, and we will discuss a distributed solution later. So centralized algorithm simply means that there is one entity that knows everything there is to know for the purpose of computing the output that we want. In particular, in this setting, in the centralized setting, the agents can just supply to the server the entire cost function, which in practice would be expensive because if the cost function is a loss function over a lot of data, then this requires you to ship the data perhaps. So that's expensive, but this is just for the sake of discussion to demonstrate the existence of a T-resilient algorithm. So the good agents provide their true cost function, the fault agents can provide bogus cost functions. Having received those cost functions and the server performs this computation, server looks for a set S among, remember there are n cost functions the server has. The server looks for a set S containing n minus T agents such that for each n minus 2T subset of that set S, the following is true, that argmin over set S is equal to argmin over set T. And if this happens to be true for set S, then we can proceed to the next step. And such a set S always exists because if you happen to choose, actually, let me just leave it there because I'm not going to prove it, but such a set S always exists. Let me just leave it there. In fact, there exists a set S of containing n minus T good agents for which this property is true. But having found such a set S, then the server simply outputs a value X in the argmin of Fi over that set S. And we can prove that this particular output satisfies the T resilience property. This X will in fact equal to the argmin over all the good agents. Okay, so this, I'm not done the proof here, but this correctness of this central algorithm shows that if you have 2T redundancy, then you can achieve T resilience. But the proof goes both ways, meaning you can also show that if you want T resilience, 2T redundancy is necessary. And so this is a tight condition. What I have not shown is a distributed algorithm. We'll come back to this distributed algorithm soon enough in this tutorial. But let's take a brief detour and discuss approximate resilience. So this is, suppose this set here, which could be simply a single unique point in general, in some cases. But let's say this yellow set is the argmin of summation of Fi over all the good agents. Now, exact resilience required that I have to output something in this yellow set. That's the requirement for exact, the resilience, the T resilience that I discussed on the previous slide. Approximate resilience relaxes this requirement a bit. Intuitively, when we were defining exact resilience, what we wanted was to output a point that is within a distance epsilon of this set. If epsilon is 0, we get the property that we just defined earlier of T resilience. But if epsilon is non-zero, then we are weakening our expectation from the algorithm. And so this is the approximate resilience that and I was alluding to earlier as well. But the exact definition of approximate resilience that we use is slightly different. And we observe that if I give you n cost functions from n agents, in principle, any T of them may be potentially bad. And so in other words, the good cost function may be any set of n minus T agents among these n agents. With that in mind, the definition of approximate resilience that we call T epsilon resilience is the following. We will say that T epsilon resilience is achieved if the output is a point within distance epsilon of argmin of any n minus T cost functions, argmin of the summation of any n minus T cost functions, not just any one particular one, but any n minus T cost function. In particular, if you have only n minus T cost functions that are good and remaining T are bad, then of course this set S is unique. But if you have more than n minus T good cost function, then there are many choices for set S, and the output has to be within distance epsilon of all of them. That's the requirement that we are setting out to achieve here for approximate resilience. And to achieve this resilience, there is a corresponding redundancy condition as well that I'm not going to try to formulate here today, but you can look at this reference here, and then there is some follow-up work to this as well that specifies a redundancy condition that if you satisfy it, then this approximate resilience can be achieved. And there is a distributed algorithm for doing this as well that I will briefly refer to later. So what we did so far is we talked about independent functions and showed that our objective was not achievable there, but perhaps you can approximate that using the weighted average of the cost functions. Or we may insist on achieving our original objective, which is exact resilience, or approximating it in this other way of finding an output within distance epsilon of where we want to be. And question is then how do you achieve any of those goals? So we are back to the algorithm that we discussed earlier, the server-based algorithm. Much of the work on fault-tolerant optimization is on server-based algorithms. There is some limited work on peer-to-peer settings. So we'll focus here mostly on on server-based algorithms so far as fault tolerance is concerned. This is the algorithm we said earlier that we are going to replace the summation of the gradients by filter gradient. And then the question becomes, what is the filter? The filter that I'm going to discuss, some of them are applied for deterministic gradients, meaning the exact gradient of the cost function, like that. So in particular, with the deterministic setting, agent I will send the actual gradient of function I to the server if agent I is fault-free. In the stochastic optimization, I think I said briefly earlier as well, agent I doesn't send the actual gradient itself, it doesn't send that, but it sends an estimate, let's call it GI, of that true gradient at the estimate xk. And the estimate is chosen so that it's unbiased. So the expected value of that gradient will be equal to the actual gradient of the cost function of agent I. And so the agent sends this gradient, and then the server has to perform filtering on this stochastic gradients instead of the actual gradients. That's what it says here. So what the agents are sending to the server are the stochastic gradients, and then the server has to apply a filter on the stochastic gradients. So there are quite a few filters proposed by this time. And I'm going to try to cover 3 or 4 of them today. But here is a grid that tries to lay out the space of the problem space. So on the one hand, in this dimension, the gradients may be deterministic of the actual exact gradients, true gradients of the cost functions, or the gradients supplied by the agents may be stochastic gradients. That's one dimension in which the solutions vary. Or there is another dimension where we have assumptions about the cost functions. So the cost functions may be identical, like I illustrated previously, or the cost functions may be non-identical. And so let's consider the grid a little bit more. So this corner of the grid is trivial, where the gradients are deterministic and the functions are identical. Like we said earlier, you can just take majority of the gradients, and that works. So this is not a particularly interesting corner to be in. The rest of them, the remaining 3 boxes in this grid are all interesting and have been studied. So The second case is that you may have gradients that are deterministic, meaning the agent actually supplies gradient of fi(x) to the server. And then you may have the setting where the functions may not be, I mean, they're not necessarily identical, but they may not have redundancy, or they may have redundancy. For the case where they don't have redundancy, we saw one filter already, but the deterministic gradient case is interesting even when you do have redundancy. Third setting, the functions are identical, but the gradients are stochastic. So what does that mean here? Basically, the stochastic gradients are you can think of the algorithm as being randomized. The stochastic gradients are random estimates of the true gradient, and they're drawn from a distribution. And the agents being identical, or the cost functions being identical, basically means that the stochastic gradients are being drawn from an identical distribution and independently across all the agents. For example, in machine learning, this can happen that the agent 1 and agent 2 basically have access to the same data sets. The data sets here are identical, and they are, in the case of training of a neural network, what the agent may be supplying is the gradient of the loss corresponding to a randomly chosen subset of the data. So for example, I don't have a picture, but agent 1 might randomly choose this data item and this data item that I tried to color in blue here randomly, whereas agent 2 might randomly pick this item and that item and compute the loss for those two items at the current parameter values. And this is what I'm alluding to here in this setting. Even though the data is identical, the gradients are drawn from the same distribution, the stochastic gradients don't have to be identical, and they typically will not be identical. And finally, in this corner, again, we have stochastic gradients, but the gradients may be drawn from distributions that are not i.i.d. They're not identically distributed or independent in general. And like I said, all these settings have been studied by now. So let's look at the various filters. The algorithm structure that I presented, you have a server, the server sends estimate to the agents upload the gradient. By and large, most of the literature uses that structure or variations on it, which I will gloss over. And what I will talk about are just the filters. So the first filter that I'm aware of is the one that I introduced already, and I'll come to it again. Here, we talked about this previously, right? We have n gradients that are scalars, because we're looking at the case now where the argument is scalar, and then we throw out the largest and the smallest t values and take the average of the rest. This particular filter has been used previously for many years in literature on Byzantine consensus, which is a simpler problem than optimization, but has relationships to distributed optimization problem. And the filter is sometimes called the trimmed mean filter. And here's an example. So let's say the server receives, in this example, 7 values, so n equal to 7, like it says here. And suppose we are trying to tolerate 2 faulty agents, t equal to 2. So what the server is going to do is to throw away the smallest 2 values, in this case, -4 and -2, the largest 2 values, 8 and 9, and then the filter gradient is the average of the remaining 3 values. This is what it's going to use in this step where it computes, let me go back, where it computes xk, where is it? Here. So this is where the computed value will be used to compute the next value of x. And then this will repeat itself. And so in this manner, the various filters are going to be used. So that's the first filter. Actually, it's been applied in a variety of settings by now, that particular filter. It was introduced initially in the work for the case when there is no redundancy, but since then it's been used for the case when there is redundancy. So for the other filters as well, I will try to identify the setting in which the filter was introduced, but even if the filter was introduced for this setting here, it doesn't necessarily mean that it can't be used here. It's just that when these filters are introduced, they're introduced for a particular version of the problem. So the original filter that I discussed earlier was for scalar arguments, but it can be naturally extended to vector arguments as well. And it has been done by now, where basically the scalar filter is applied element-wise to a vector. I think I have an example of that too. So let's say number of agents is 4, n equal to 4, t equal to 1, dimension of the vector is 3. And so what we're going to do is to apply the filter to the first element, then to second element, and the third element all separately, independent of each other. And the red values are the outliers in each of the dimensions. And then, for example, the first dimension, we throw out -1 and 7. We throw out that, we throw out that. And the average of 0 and 6 is 3. That's how I get 3. And similarly for the remaining 2 dimensions. So the filtered gradient is equal to that. That's what will be used for computing the next estimate. This filter is different from a filter that's been used in previous work on something called vector consensus. This is not, the vector consensus is a filter that operates on the vector as a whole, not each element separately. And so it has a different behavior than the filter we are discussing here. In fact, this other filter, which I'm not going to introduce in detail today, has also been used in the work on distributed optimization. So if you want to look for that filter, look for the work on vector consensus or Byzantine vector consensus. And you will find a paper that's in fact co-authored by me. And you can see the filter that's used there, which is also useful in the work on Byzantine optimization.